today's video is going to focus on solving the heat equation. So we are going to focus on this problem right here. So we are interested in solving this boundary value problem. This is our heat equation. So we have our rod of length L and our time is positive. Remember, what we're doing is we are looking for U of xt, which represents the temperature at some position x and time t in the rod. So that's what we're solving for, is that U of xt. We have these two conditions here. Those are boundary conditions. And so what those tell us is that both ends are held at a constant temperature 0. And so what that does is that makes our equation homogeneous. And then this third one is our initial temperature distribution. And we can tell that because we have this time 0. One quick note before we solve this is this equation, just so you know, you might see it expressed as k of u xx is equal to u of t. That's the same equation. So that's the same equation. So what we're going to do is we are going to try to solve this by separation. So we are going to assume that our u of xt is a product of a function of x and a function of t, rather. So then if you remember, I prefer to just write that as big X and big T, and we're just going to keep in mind big X is a function of X, big X is a function of T. And so what we're going to have to do is we're going to have to find the second partial with respect to X and the partial with respect to T, and we're going to have to substitute that in. So where that gets us to then is we get K X double prime of T is equal to X T prime. And again, keeping in mind x and t are both functions. Okay, so if we separate this, we're going to get x double prime over x is equal to t prime over k of t. And if you remember, we set this equal to negative lambda. Okay, so then if we take this and set it equal to negative lambda and this and set it equal to lambda, it's going to give us two different equations. So we will get x double prime, add lambda of x equals 0, and we'll get t prime, add k lambda of t is equal to 0. Now, when we've solved this before, we know that there are 3 cases for the solution, depending on the value of lambda. So we know that lambda could be equal to 0, lambda could be equal to some negative number, or lambda could be equal to some positive number. And we've already solved each of those before in an earlier video. When lambda is equal to 0, we get x to be c1 add c2x. If lambda is negative, then we get our x to be c1 e to the negative lambda x, add c2 e to the, not lambda, alpha. And then lastly, if lambda is positive, we get x is equal to c1 cosine of alpha x, add c2 sine of alpha x. Okay, so what we're going to do at this point is we're going to go back and we're going to look at these conditions. So we're going to look at these conditions right here. So if we return to 2, we know that u of 0t is equal to 0, and we know that u of lt is equal to 0. Okay, so this u of 0t, that's really x of 0 and t of t is equal to 0. And then this other condition, our u of lt, so that tells us that x of L and t of t is equal to 0. Well, we really don't want t of t to be equal to 0, right? That would give us a solution that we don't really care about. So we don't want t of t to be equal to 0. So what that gives us then is that x of 0 is equal to 0 and x of L is equal to 0. So this part right here, x of 0 is equal to 0 and x of L is equal to 0. That's the only way that those equations in red would be true. That's pretty convenient because what we can do is we can now return to our 3 cases. For that first case, if lambda equals 0, if we were to substitute in x of x equals 0, that would give us u equals 0. If we look at the case where lambda is negative, and we were to substitute in x of x equals 0, you would also get u equals 0. You just need to trust me. The only time that's not the case is when lambda is positive. If we substitute in that x of x equals 0, we get c1 equals 0. So then if we take x of L is equal to 0, that gives us 0 is equal to c2 sine of lambda L. Well, we don't really want c2 to be 0 because that would give us a trivial solution. So instead, we get sine of alpha L is equal to 0. Well, that happens if alpha L is some multiple of pi. So what that gives us then is that alpha is equal to n pi over L. Okay, so let's do a little bit of regrouping and make sure that we understand what we found and where we currently are. So what we know so far is that we have non-trivial solutions when lambda, which is equal to alpha squared, is equal to n squared pi squared over L squared for n equals 1, 2, 3, so on and so forth. Okay, have you seen these before? Hopefully you recognize that. These are eigenvalues. Yeah, they're coming back. Okay, so finally, where that gets us then is that x of x is equal to c2 sine of n pi over Lx for n equals 1, 2, 3, so on and so forth. Again, you've seen this. How exciting. These are eigenfunctions. Okay, so we have our x of x. We're not done yet. If we look above, we still need to figure out what is our t. Okay, so I'm going to continue with t on the next page. So now we're going to go to our second equation. Our second equation being that t prime add k lambda t is equal to 0. Okay, well, we can solve this by separation. We get t prime over t is equal to negative k lambda. So we are integrating with respect to t, because remember, these are functions of t. So what we get then is we get natural log of t is equal to negative k lambda t add some constant. So we get our t then to be c3e to the negative k lambda t. We know, though, what this lambda is. We already found that lambda on the previous page. So what this gives us is that t is equal to c3e to the negative k, while our lambda is n squared pi squared over L squared times t. So at this point, we said we want our u of x to t to be some function of x and some function of t, the product of those two. So if we take this function that we have right here and the function from the previous page, our u of xt then is just some constant that I'm going to write as a of n. That's really just c2 times c3. And then we have e to the negative k n squared pi squared over L squared t sine of n pi over Lx. So again, let's do a little regrouping at this point. Each u of n, because this is really n, it's based on the value of n, is a solution of the equation. That's what 1 is. And it satisfies those second conditions. Now we need to look to condition 3. So the only condition we haven't used so far is the initial temperature distribution, which looks like this. Okay, so if we look at our equation from above, so our u of xt, this whole thing, and if we think we substitute in 0 for t, we're going to have e to the 0, which is just 1. So that would just leave us with a of n sine of n pi over Lx. Okay, at this point, if we think reasonably, we won't be able to find a reasonable f of x to satisfy this. But by superposition, we know that u of xt, which is what we're looking for, is the sum from n equals 1 to infinity of u of n, which is the sum from n equals 1 to infinity of that a of n e to the negative k n squared pi squared over L squared t sine of n pi over Lx. So we know that this does satisfy 1 and 2. Okay, well, how is that helpful? So where that leads us to then is that u of x0, which is equal to our f of x, that's really just the sum from n equals 1 to infinity of a of n sine of n pi over Lx. Okay, does this look familiar? Yes, this is another throwback. It should look familiar. The way you saw it before, though, was like this. N equals 1 to infinity of b of n sine of n pi over Lx. If you remember, this is a half-range expansion. In a sine series. So if we think back to that sine series, how did we find this b of n, or how do we find this a of n? Well, that a of n, which before we've seen as b of n, that was 2 over L, the integral from 0 to L, of f of x sine of n pi over Lx dx. So finally, where this leads us to, our u of xt, the solution that we're looking for, which we've written before as a of n e to the negative k n squared pi squared over L squared t sine of n pi over Lx. That becomes, since I ran out of room, I'm just going to say it becomes what's in this box. So you're going to see we have that e to the power, we have that sine of n pi over Lx, and then this a of n, which we wrote up here in red, is this 2 over L, and then our integral. So all of this is the solution to the heat equation. There is a special case for us to just chat about real quick before we look at our first example. If we think of the special case where u of x0 equals 100, sorry, that should be equals 100, and L is equal to pi and K is equal to 1. Okay, so what this is telling us is that our initial temperature, so at time 0, no matter the position, our initial temperature is 100. And that if the length of the rod is pi and K is equal to 1, then you can verify this. A of n would be equal to this, so u of xt is equal to that. Now, that's a fun fact. Do you really need to know it? No. What you need to know is this solution. So this is the solution that you either need to be able to memorize or to generate yourself. Okay, we are only going to be doing one example together. So let's take a look at an example on the next page. Example 1, find the temperature u of xt at any time in a metal rod that is 50 centimeters long, insulated on the sides, which initially has a uniform temperature of 20 degrees throughout, and whose ends are maintained at 0 degrees for all T is greater than 0. Okay, so I want to repeat, this is the only example that we are doing together in this video. So please make sure that you are on your A game, your full brain is ready to go through this. First thing that we're going to have to be able to do, of course, is write what the problem is that we're actually solving. This is a heat equation. So we're going to start with the heat equation. So second partial of U with respect to X is equal to the partial of U with respect to T. And we know that time has to be greater than 0. We also know that our rod is 50 centimeters long. So that says for our domain that X has to be between 0 and 50. And again, that 50 is our L. Okay, next thing we know, it has an initial temperature of 20 degrees throughout. So that means no matter the position at time 0, we are held at 20 degrees. And we are also told the ends are maintained at 0 degrees. So at position 0, no matter the time, we have a temperature of 0. And at a position of 50, so it's not L, it's the end of the rod, doesn't matter the time, we're going to have a position of, or a temperature of 0. So labeling some of these things, again, 50 is that L. And this 20, that is our initial temperature distribution, that is f of x. Okay, so what we saw on the previous page, what we derived, our u of xt is going to be 2 over L, the summation from n equals 1 to infinity, the integral from 0 to L of f of x, sine of n pi over L x dx, and then we're going to have e to the negative k n squared pi squared over L squared t sine of n pi over Lx. Okay, so looking at this, where should we start? Well, we should probably start with this integral. So this is going to be the integral from 0 to 50 of 20 sine of n pi over 50 x dx. So this is 20, and if I integrate that sine, I get negative 50 over n pi cosine of n pi over 50x, being evaluated from 0 to 50. So that gives me negative 1,000 over n pi, and then I have cosine of n pi, subtract cosine of 0. Further simplifying, this is 1,000 over n pi. Because I took this negative out, I'm going to switch these two. So I get 1 subtract cosine of n pi. That cosine of n pi we've seen before. So this is 1,000 over n pi. That cosine of n pi is negative 1 to the n, right? It's odd when, it's negative rather when n is odd. It's positive when n is even. Okay, so what this gets us to then is our u of xt is 2 over 50, the summation from n equals 1 to infinity of 1,000 over n pi, 1 subtract negative 1 to the n, e to the negative k n squared pi squared over 2,500 t sine of n pi over 50x. And then I'm just going to clean this up a little bit, pulling anything out of the summation that I can. So the summation has an n, so anything with an n has to stay in that summation, which is all of this stuff. But if I take a look at all of these constants and just simplify that a little bit, make it look a little bit nicer, this gives us u of xt is equal to 40 over pi, the summation from n equals 1 to infinity of 1 subtract negative 1 to the n over n, e to the negative k, n squared pi squared over 2,500 t sine of n pi over 50x. So this right here is our solution. Now, you should see that the vast majority of this video was deriving the solution. Using the solution, not that bad. right? All we had to do was really solve for this function here and then plug it in. So it's not going to take as long as what we think it's going to take. Few things to talk about. One thing I want to point out is we have this large negative exponent here. So this large negative exponent means that this is going to converge pretty quickly. Okay, so we have a figure to look at on the next page, but before we look at that figure, there's a few quick notes I need us to write down, or things that I need us to know. The first one is that your book or WebAssign mostly covers problems where x is between 0 and L. So you're not going to be given a value for L. So your equation would just be in terms of L, or your solution would just be in terms of L, and it wouldn't have a number in it like that 50 or that 2500. And then the other one that is a really big deal is you're going to do the same process. And by same process, I mean the derivation. So that separation that we did for problems of this type. You might still have that k, well, you're still going to have the same problem. It's the conditions that are going to be different. So if you remember, we could also be told that the partial of u with respect to x at x equals 0 is equal to 0, and the partial of u with respect to x at x equals L is equal to 0. So this is telling us that the ends of the rod are insulated. So no heat is coming in or being lost from either end. So when you see this 0 is what is important. That 0 is what tells us that this equation is homogeneous. And in this case, you would have to do that separation again. You can't just jump to the solution that we found. So I'm going to give you a heads up that this homework only has 3 problems on it, and that's because these problems are long. So you're going to have to do some really good self-reflection to determine how well do I know this? Do I need more practice? So last thing that I want to do before we move on is look at the figure on the next page. So there are some things that are interesting here for us to see. Here's the first one. This gives us temperature distributions for several times using just the first 5 terms of the series. So for example, at time t equals 300, these are the positions. So we would see the temperature is highest at this position right here. We're going to notice at position 10, this is our temperature. So we can see as time is increasing, our temperature in general is decreasing. Now, similar idea over here. This time we have temperature profiles as a function of time at several different locations. So in this case, this x equals 25 is a position 25, and here is our time. So as time is going on, here's our temperature. As time is going on at this position, the temperature is decreasing. And in fact, at all of the positions, the temperature is decreasing. And this right here is the plot of temperature. And then this note at the bottom we already wrote on the previous page, so I'm not going to rewrite it. So that was the heat equation. You can probably guess that the next and last video that we will be doing is solving the wave equation. So until next time, thank you for sticking with me.